Welcome to this video on estimating errors using uncertainties. This is a second in a series of 3 videos, so if you'd like to watch a video on accuracy and the concept of error, click the appropriate link. And if you want a worked example of how this works out in practice, then click the appropriate link. Furthermore, if you want a summary of the important formulae for doing this, then if you can click the link in the description, you should be able to find that and go straight to that part of the video. So we're in this question asking, how can we work out how accurate is my experimental result? And the answer is we're going to use something known as uncertainty. So here is the problem that we're faced with. We have recorded a volume, let's say it's a titer in a titration experiment, and we want to know how accurate is that value. But the problem is that in order to work out the error, we need to know the true value. So we introduced in the previous video this formula for working out the percentage error, and it required us to know what the value actually was. The problem is usually I don't know what the true value actually is, and so I can't use that formula. So the solution to this is to use something called an uncertainty. And the uncertainty is an estimate which you attach to a test result, which characterizes the range of values within which the true value is asserted to lie. So rather than just quoting a volume as 9.1, I actually say that the volume should be 9.1 plus or minus 0.5, and this 0.5 is the uncertainty. 9.1 was my test result. That's what I calculated the titer to be. But actually I'm saying now I don't know that it was exactly 9.1. It's a little bit fuzzy. And so the uncertainty characterizes the range of values. So we're basically saying here that we could have the lower bound of my titer could be 8.6 centimeters cubed, and the upper bound could be 9.6 centimeters cubed. I'm not that sure anymore. I'm saying that somehow my titer could lie between 8.6 and 9.6 centimeters cubed. And I assert that the true value, which I don't know, is somewhere in that range now. So a small uncertainty means that we have a low error. So if we've got a small uncertainty, we're saying my test result is very, very close to the true value, or that there's a very small range of values in which the true value lies. So small uncertainty means low error and high accuracy. And from the first video, we saw that that's exactly what we want in an experiment. So what we want to do now is actually look at seeing how can we calculate the uncertainty in a given experimental situation. There are a couple of challenges facing us. The first challenge is the causes of uncertainty. Now, uncertainty in principle should take account of random effects and systematic effects. And if you're not sure what they are, watch the previous video in order to find out. Now, we actually focus in A-level chemistry on the random effects arising when measurements are made, because we find that relatively easy to do, and so therefore known as measurement uncertainties. And later in this video we will see how systematic effects can sometimes be uncovered by this approach. The second issue is, how do we actually find the overall uncertainty? Now, equipment will often state its uncertainty on it. So if you use a pipette, that's a 25 milliliter pipette, then it will say on the side that this is the uncertainty of plus or minus 0.06 centimeters cubed. But that's only one bit of equipment that I use. So how will this uncertainty affect the test result, the final titer or concentration or mass that you calculate using the volume measured by that pipette? And what we're going to see is that whilst we can't combine these uncertainties here directly, we can use something called the percentage uncertainty to combine uncertainties. Now, at this point it's important to mention that that's actually an approximate approach which isn't always used. And when you get to higher levels of study at university, you'll probably use formulae called propagation of uncertainty formulae, which provide a more rigorous way of combining the uncertainties from different measurements. So the first stage in all of this is to determine what are known as the absolute uncertainties from the equipment that's been used. Now, sometimes this can be estimated from the spread of data, but this is not done in A-level chemistry. Instead, you estimate it simply by considering the equipment that you've used. And it's important to note that these values are given for making a single measurement, and we'll talk about multiple measurements using the same bit of equipment in a moment. So how can I find the uncertainty? Well, the first thing to look for is to see if the equipment actually says on it what the uncertainty is. So for example, a 10 centimetre cube pipette will say its uncertainty is plus minus 0.04 centimetres cubed. A 100 centimetre cube volumetric flask may have an uncertainty, as some that we used in school, of plus or minus 0.2 centimetres cubed. So first thing to do is to look on the equipment. Second thing to do is to think about, if it doesn't say it on the equipment, if you've got apparatus with a scale, then the typical uncertainty is plus or minus half the smallest graduation. So for example, in a burette, we have the graduations going every 0.1 centimetres cubed. So this would say the reading would be 10.0 there. The next one is 10.1. So these graduations are 0.1 centimetres cubed apart. Half of that is 0.05 centimetres cubed. Now some glassware that's less good than a burette, say Class B glassware, says the smallest graduation. So if in doubt, again, look carefully at the equipment and see. But if in doubt, if there's nothing stated, you can assume half the smallest graduation. Now in the case of digital apparatus, there is no scale. The digital apparatus is things like a balance, where instead of having a scale, you see a readout. So you might have 0.00 grams reading on your balance. Well, the rule of thumb there is that the uncertainty is plus or minus the resolution of the equipment. In other words, the smallest measurable change. Now the smallest change that this balance can measure is 0.01 grams. Now at this point I just want to note that sometimes people say it's half the resolution, and to my mind that actually makes a bit more sense, but currently in A-level chemistry, at least with OCR, it's plus or minus the resolution. So if you're not doing OCR, I suggest that you check carefully exam board documentation to see what you should use. What about multiple measurements? And these are actually really common, so-called measuring by difference. You might measure the mass of something before, then add a chemical and measure the mass after. You might measure a temperature change from temperature before and after. And commonly in titration analysis, you measure an initial burette reading and a final burette reading, and the difference between those two gives you the titer. And the key here is to recognise that this time the absolute uncertainty is multiplied by 2. And the reason for that is because the first time you take a measurement, you're going to have a certain amount of uncertainty, and the next time you take a measurement, you're also going to have the same uncertainty. And so actually you double up the uncertainty in your measured value. And that even occurs if you're actually subtracting as well as adding. And this same reasoning applies if you take more than 2 measurements with the same equipment. So let's say you used a measuring cylinder 5 times to put in the volume required. You'd actually have to multiply the uncertainty by 5 times, because every time you measure it, you incur an uncertainty. Once you've got the absolute uncertainty sorted, again, just like with percentage error, it's much better to work out the percentage uncertainty, which is simply measuring the absolute uncertainty as a percentage of the value you measure with the equipment. And this is the formula that you're going to use. You take the absolute uncertainty, taking account of any doubling or multiplying factors, you divide by the measured value, and you times by 100. So from this formula, it makes total sense. The percentage uncertainty will be larger if the absolute uncertainty is larger, or if the measured value is smaller, which is why it's always worth trying to measure a fairly large value with your equipment if you can. And the final thing to note here is that when you're measuring by difference, the measured value is the difference, i.e. the value you take forward from the apparatus to use in calculations. Third step is to combine percentage uncertainties. So in some experiments you've got several quantities being measured with different units, and they're combined to give the test result. So you can't just add together uncertainties in absolute terms, because they've got different units, and you can't add things with different units. So instead what you do is you combine the percentage uncertainties by simply adding them together. only include quantities that you've measured which matter in the final result. So for example, if you measure the volume of something which is going to be in excess, you don't need to include it. And if you measure something approximately, again, you don't need to include it. So the simple rule of thumb would be you include the uncertainties from equipment which you've measured quantities that you then use in your calculation to find the test result. So if something was in excess, you didn't use it in the calculation, you don't need to include it in the total percentage uncertainty. Fourth and finally, once you've got the overall total percentage uncertainty, you need to convert it into the same units as the test result. Because remember, what we were trying to do is come up with an uncertainty which is in centimetres cubed here. So what we want to do in this case is use the following formula. We take the percentage uncertainty and divide by 100, and that's basically giving us the sort of fractional uncertainty. Expressing that percentage as a decimal, and then you multiply it by the test result. So let's say the total uncertainty is 5%, the overall uncertainty is going to be 0.05 times the test result. So if you've got a big test result, you'll end up with 5% of that value, and if you have a small test result, you still get 5% of that smaller value. In summary then, you start with the absolute uncertainties, taking account of any doubling needed from multiple measurements. You then calculate the percentage uncertainty. You add these percentage uncertainties together to get the total. You divide that value by 100 and times by the test result, and that gives you the overall uncertainty for your equipment. Finally, we want to talk about uncovering systematic errors using uncertainties. Now, so far, this procedure has given us what we call the measurement uncertainty. How can we use that to find systematic effects? Well, here's how we do it. Let's say we're doing a titration and we work out that the true value for the titer is 10 centimetres cubed. Two students have had a go at doing the experiment. One got 9.1, the other got 10.2. They both work out that their 10.1. They both work out uncertainties are worth 0.2 centimetres cubed. So what does that actually mean for their measurements? Well, what we said about the uncertainty is it gives us a range of values in which you think the true value lies. So for student A, actually, after the uncertainty analysis, they're saying, I think my value lies between 9.3 and 8.9 centimetres cubed. Whereas for student, oh, I've got these the wrong way around. This should be student A, and this one here is student B. Apologies. Student A is actually 10.1. With the same uncertainty, they're saying that's somewhere between 9.9 and 10.3 centimetres cubed. And they're saying, I think based on my equipment that I have used, the true value is somewhere between these ranges. But in this case, we happen to know the true value is 10. And once the overall uncertainty is known, you can find the range. And if the true value lies within the range, as it does for student A, then what you can conclude from that is that student A didn't have any systematic errors, because just this uncertainty from measurements allowed them to find a range of values in which the true value lay. Or put another way, the range of values that they have obtained contains the true value, and therefore, based on the limitations of their equipment, they may have actually worked out the true value. They couldn't do any better based on their equipment. So if the true value lies within the range, no systematic errors are present. If that happens, you get a good idea that student A has done things properly. If the true value lies outside the range, as you have with student B, then systematic effects must be present. even accounting for the fact that B's equipment wasn't perfect, B is asserting that the value should be between 8.9 and 9.3, but actually they're out still by a good amount, even considering that uncertainty bound. And therefore there must be some additional error which is causing this drift, and that would be a systematic error. Now this analysis only works if the true value is known, which, as we started the video in saying, most of the time you don't. But actually this can really help you, because if you actually come up with a new experimental procedure, you should test your procedure on a case where the true value is known before using it to find an unknown value. So if you're trying to find out a value for absolutely anything, test your method on something which you know the answer. And if your method gives you that answer to within the uncertainty bound, then you can be sure that you don't have any systematic errors. If your method cannot even reproduce a known value, then you've got problem with systematic errors. You need to redesign, you need to recalibrate before you think about using it to find an unknown value.